Hello, my name is Preston Haffey, and I'm here with Sepida Abijay, and we're PhD students who work with Rehana Savavinani on a project called Privacy Preserving FairSwap, Fairness and Privacy Interplay, done at the University of Calgary in Canada. To begin, we'll introduce the fair exchange problem. So imagine we have a seller who has a file that they would like to sell for a certain price. Then we have a buyer who's willing to pay for the file, but only if it satisfies their preferences. When the buyer and seller communicate over an open network, both parties need to trust the other to follow through on their half of the bargain, which is not a realistic assumption in many cases. This motivates the requirement for a fairness property in the exchange, where both parties are guaranteed that they either receive exactly what they asked for, or neither of them loses or gains anything from the exchange. In many exchange scenarios, fairness has been proven to be impossible to achieve. We can ensure fairness, though, with the help of a trusted third party, referred to as a TTP. The idea is that both parties send their half of the exchange to the TTP, who checks that the conditions of the exchange are met. If everything checks out, then the TTP can send the file to buyer and payment to seller. Or if some conditions of the exchange are not met, the TTP can ensure buyer doesn't get the file and seller doesn't get payment. Next, I'll just outline the rest of the presentation. So first, we'll talk about smart contract-based fair exchange and the original protocol FairSwap. We'll talk about the information leakage we found in FairSwap and its effect on fairness. Then we'll discuss our approach to dealing with the information leakage and present our protocol for private FairSwap. Then we discuss our implementation results and then conclusion and future work. The authors of FairSwap protocol point out that finding a truly trusted third party is very difficult. Blockchains are readily available decentralized networks that provide trusted state information and program execution. They can maintain a trusted ledger of transactions, but also a virtual machine inside which programs called smart contracts can be executed in a transparent and trusted manner. This lets us encode the preference checking and the currency transfer functionality of the TTP as a smart contract that can be compiled and deployed to the blockchain. Now, buyer and seller can conduct their exchange to the trusted blockchain network. However, blockchains have serious limitations when it comes to storage and computational capacity. FairSwap's approach is to perform the item transfer and preference checking off the blockchain network, and then use the smart contract to verify and settle any disputes if one occurs. The buyer's preferences are checked with a circuit. The file is fed as input to the circuit, and the circuit outputs 1 if the properties are satisfied and 0 otherwise. If there's a problem, the buyer can complain with something called a proof of misbehavior. In FairSwap, we have 3 phases. The initialization phase sees that the seller runs the property checking circuit on their digital item and encrypts all of the steps of this circuit computation. They then store the commitments to the item, the circuit execution, and encryption key to the smart contract. The buyer's funds are also locked by the contract. Then the seller sends the encrypted item and circuit execution to the buyer. In the reveal stage, the seller reveals the encryption key, allowing the buyer to decrypt and verify the circuit computation. In the payout stage, if no complaint is received by the smart contract, then the smart contract releases the coins back to the seller. If a POM is received and verified, then the contract refunds the coins to the buyer. It might be the case that the seller forces a gate to misbehave, causing the circuit to output a 1 on an incorrect file. In this case, the buyer can find the misbehaving gate and construct the proof of misbehavior. This includes the gate operation, the inputs to the gate, and the output to the gate, along with Merkle proofs that show that this information is related to that was committed by the seller in the initialization stage. Now I'll pass it on to Sepida.
Hello, my name is Sepida, and I will continue the presentation. We observed that proof of misbehavior, or POM in short, which is created by the buyer in the dispute resolution stage, leaks the inputs and output of one gate to the smart contract, and it leads to privacy breaches. The question is how important this leakage can be and whether there is any issue with the fairness guarantee of the protocol. Let's consider that the corrupted gate is in the input layer. Then you see proof of misbehavior leaks the input data corresponding to that gate to the public eyes. If the predicate is represented by Boolean circuits, the leakage is as small as 2 bits. But if the predicate is represented by an arithmetic circuit, then the leakage can be huge, as it is 2 gamma, where gamma depends on the security parameter. When the confidentiality of the input data is necessary, then proof of misbehavior creates problem. Moreover, this leakage can affect fairness. For example, in the case that the item is associated with the buyer's personal information, a malicious seller can send the buyer an item which doesn't satisfy the required predicate. For example, a file with a lower quality than expected. If buyer intends to complain about the file, her personal information will be leaked. And this leakage can be used to link the item content to the buyer. This can put the buyer in a dilemma whether she has to complain and sacrifice her privacy, or she has to accept the wrong file and sacrifice the fairness. Also, a malicious buyer can put the seller in a position that he accepts a lower price only to prevent the partial leakage of data to the public. As this leakage can affect fairness, we add the smart contract privacy as another requirement for a smart contract-based fair exchange. This means that the smart contract, who is a non-exchanging party, only learns negligible information about the exchange. To provide this property for FairSwap, we can consider different solutions. For example, one simple solution is to restrict the predicate to be represented by Boolean circuits, just to limit the leakage. But this is not practical, as some predicates cannot be efficiently implemented as Boolean circuits. Another solution is using homomorphic encryption for the item and run the predicate on the encrypted file. However, this incurs a huge computation cost on the smart contract and the seller. The approach that we take is motivated by the randomized circuits, with probing security in the context of side channel protection. The idea of randomized circuit was proposed by Isha et al. In 2003, and their solution protects the Boolean circuits against a probing attacker who can observe L wires of the circuit. L is known in text. The solution expands the circuit by using secret sharing. Each wire in the circuit is transformed to two L+1 wires, where each wire carries a random value, and probing L wire cannot leak any information to the probing adversary. In FairSwap, the smart contract always sees the information of one gate, 3 wires, so we can model the adversary as a probing attacker and use secret sharing as a solution. For practicality, we extended the randomized circuit to the arithmetic circuit. We set L to be 1. The reason is that the input and output wires of one gate are not independent, and we showed that it is enough to set L to be 1. Note that when the wires are expanded to 2L+1 secret shares, we need to replace the gates with the gadgets, where each gadget includes several arithmetic gates by itself. This is because we have to make sure the gadget will generate the secret shares of the original output when we give secret shares of the input, and the leakage of L wires correspond to a negligible information about the original values that are carried by wires. So for the multiplication gates, it is necessary to have random gates, which take random values. To adopt FairSwap with randomized circuit approach, we need to modify the protocol at 2 stages. In the initialization stage, the seller and the buyer engage in choosing a random seed for a pseudo-random number generator. From this seed, the seller generates all the required randomness and expands the circuit using secret sharing, and then he replaces the gates with their corresponding gadgets. Seller also commits to the transformed circuit and used randomness in the smart contract. In the dispute resolution stage, the buyer generates the proof of misbehavior on the expanded circuit. For efficiency, buyer can run the original predicate on the item, but after the corrupted gate is detected, she must generate and send the proof of misbehavior on the randomized gate. The smart contract can verify the correctness of proof of misbehavior and detect misbehaving party by running the computation of one gate with random inputs. We use generalized UC framework to show the security and privacy of our scheme. We showed that the buyer fairness is satisfied, meaning that if buyer is honest, either buyer receives correct item or doesn't lose any coins. Also, seller fairness is satisfied, meaning that if the seller is honest, either the seller receives the coins or doesn't reveal any information about the item to the buyer. To show a smart contract privacy in 2 cases, when there is no disputes and when there is one malicious party, and proof of misbehavior is generated and published to the smart contract, we use the concept of non-monolithic adversaries that was introduced for server-aided MPC by Kamara et al. We model the smart contract as a semi-honest and independent entity in the protocol rather than an ideal functionality, and showed that the leakage to the smart contract is negligible.
To compare the on-blockchain and off-blockchain computation between FairSwap and private FairSwap, we implemented the relevant parts of both protocols. We wrote the smart contract in Solidity and deployed it to an Ethereum testnet. The circuit randomization and proof of misbehavior construction was written in Python. We executed both protocols with a UTF-8 encoded version of The Raven by Edgar Allan Poe for 3 different circuit sizes. We found that circuits in private FairSwap were 10 times bigger than in the original FairSwap, and there was only a slight increase to the work done by the smart contract in private FairSwap compared to the original FairSwap. To conclude, we talked about our observations of leakage in the proof of misbehavior. We also talked about privacy of a fair exchange in the smart contract setting being affected by having its fairness affected. And we introduced our privacy preserving FairSwap using circuit randomization. For future work, we'd like to work at optimizing the private FairSwap protocol. One of these ways could be to avoid the full decryption and verification of every value in the encrypted circuit execution. And we can also optimize the circuit description where we could have private circuits that include higher level functions for the gates. Thank you. We'll be happy to take any questions now.